So, good afternoon, everybody. Welcome to the afternoon session of the first day of this workshop. So, we're very happy to have Thomas Mertens from Ghent University opening this session. He'll be talking about bulk observables in JT gravity. As usual, during the course of the talk, if you have any questions, feel free to unmute yourself and ask. Okay, so Thomas, it's all yours.
Yes. Thank you. So first, let me thank the organizer for inviting me to give this talk at this wonderful workshop. So I'm going to talk about bulk observables in Jacques-Teilboom gravity, and my talk will be roughly based on these papers and also some work in progress that I will mention near the end. So first, a brief outline of my talk. I will, of course, start by introducing the model and explaining why I think it's interesting. And then secondly, I will come to the main part of my talk, which will be to compute bulk observables, and in particular, their correlation functions. I will mainly talk about the bulk 2-point function. And then I will apply this to analyze the physics of the Unruh heat bath in this model. And then, of course, I will end with some conclusion. So let me first briefly introduce the model itself. So Jacques-Teilboom, or JT gravity, is a specific model of two-dimensional dilaton gravity, and I've written down the action here. So it consists of a dilaton field phi that's being directly coupled to the Ricci scalar. There's also this +2 here. This corresponds to a negative cosmological constant because I will be interested in studying this model in ADS for holographic purposes, obviously. And also because we will have a holographic boundary, I will add this Gibbons-Hawking-like boundary term here. Now, why is this model interesting, or why has this model attracted considerable attention in the past couple of years? So there are several reasons. First, it is the dimensional reduction of three-dimensional pure gravity with negative cosmological constant, so in the S-wave sector. Secondly, it appears as the near horizon theory of near extremal higher dimensional black holes, so it has some universality to it near the horizon of higher dimensional black holes. And then thirdly, and this is how it appeared well in 2015 during Kitaev's talks, it describes the low energy sector of all known SYK-like models. Another reason is that it's exactly solvable, at least at the classical level, and also, well, to a large extent at the quantum mechanical level, and this is what I will talk about. And this includes the coupling to bulk matter fields. And then finally, a very recent motivation why this model is interesting is that because in this specific model, we have an understanding of the role of higher genus contributions to the gravitational path integral, and even beyond that to go to non-perturbative effects in the genus expansion. So this is thanks to this wonderful work from Schenker and Stanford from last year. So my goal of this talk here will be to discuss the bulk quantum gravity physics that this model contains. So let's now try to imagine inserting this action in a path integral calculation. So well, once it's in the path integral, we path integrate over the dilaton field and the metric. So the dilaton field only appears as a Lagrange multiplier. So we can directly path integrate this out, and we get that R equals -2 off shell. Now in 2 dimensions, this is sufficient to characterize the geometry as some patch of the ADS2 geometry. So what I've written here, the metric, the Poincaré metric on the ADS2 geometry. I have chosen big Z as my Poincaré Z coordinate that ranges from 0 to infinity, where Z equals 0 is the holographic boundary. And I have called big F my Poincaré time coordinate. This notation will be obvious later on. So now, well, now that we know that the geometry is ADS2, I think it's interesting to first briefly recall several classical important frames or patches of the ADS2 geometry. So to describe these, I transferred to light cone coordinates. So F and Z were the Poincaré coordinates. So U and V are these light cone. Yes.
Sorry to interrupt. Before you describe this, in this path integral, what are so there's a boundary, as you said. So what are the boundary conditions on the?
I will come to that. I will come to that. It's on 2 slides. Okay. Okay. So well, before describing the boundary conditions and solving this model, I'll first briefly review some of the classical patches or frames you can put on the ADS2 geometry. So of course, the Poincaré patch, that's just the patch that I described on the previous slide. It's just like that. And you can find this 2-dimensional geometry in the near horizon regime of an extremal higher dimensional black hole. Well, of course, as is well known, this metric has SL2R isometries acting in this Möbius transform way on the separate light coordinates. Now, there is a second important classical frame you can put on the ADS2 manifold that will be important for our purposes, so that's why I have it here, which I will call the black hole frame. And this consists of using a chiral transformation on these u and v coordinates in terms of a small u and small v coordinate. And I have defined a parameter beta in doing this transformation. Plugging that in the Poincaré patch, you find this geometry. And this geometry is found in the near horizon regime of higher dimensional near extremal black holes, where of course this beta parameter is just the inverse temperature and it's proportional to square root of the mass of this higher dimensional black hole. Now, just to give you a graphical representation of this, I've drawn the Penrose diagrams here. So the big white region is the global frame, or is the strip of the ADS2 manifold. Then this big triangle is the Poincaré patch, and then embedded within that is this black hole patch. Okay, so now let's continue with our main story. So we have path integrated out the dilaton field phi. Now this removes entirely the bulk contribution, and then only the boundary term survives, only this Gibbons-Hawking boundary term. Now, as boundary conditions, we will choose the following. So we will consider a boundary curve f of tau, z of tau, so the Poincaré coordinates as a function of some new proper time coordinate tau, as UV cutoff of this space, and this carves out the shape from the ADS2 geometry. And then how do we choose this boundary curve? Well, I will impose two conditions. The first is that along this boundary curve, we preserve the asymptotic Poincaré geometry. And this relates this z of tau function to the f of tau function in this way, where epsilon is some infinitesimal number that, well, is regulating the z goes to 0 boundary. So this is the standard thing you do in ADS-CFT. This is basically Pfefferman-Graham gauge, leading order. Now, what is new in this setup is that in addition to that, I will also impose a boundary condition on this dilaton field phi, and I will demand that it follows a constant large value. So I have parameterized this large value of the dilaton here as a over 2 epsilon. So this epsilon is the same as here. And this a is some new dimensionful constant that defines my theory, that defines this boundary condition. So these are the boundary conditions that we will impose. And now you can explicitly compute this boundary action. You have all of the ingredients you need. So you can compute this square root of the pullback metric here is just 1 over epsilon. And you can compute the extrinsic curvature trace very explicitly because you know the geometry is ADS2 with this wiggly boundary curve that satisfies these conditions. So you can just compute the extrinsic curvature trace and you find that it looks like this. Plug that back in this boundary action, then you can subtract a term, well, a divergent term by holographic renormalization, and you find that this Gibbons-Hawking term reduces to this strange looking action, where this is where the Lagrangian is the Schwarzian derivative of this F field as a function of tau. And I have introduced this big C coupling constant here. It is, well, you find it by combining this A value of the dilaton field with the 1 over G Newton that was present in the action to begin with. And this serves, or this, well, this is an effective coupling constant of this theory. And this theory is called the Schwarzian theory, which was found a couple of years ago, roughly simultaneously in these papers. Now, you should compare this type of argument to the Chern-Simons Wessel-Minowitten topological duality, where the large gauge fields in Chern-Simons theory become the dynamical degrees of freedom of the Wessel-Minowitten theory living on the boundary. So it's the same that happens here. You have the large diffeomorphisms, which would be boundary reparameterizations, that become dynamical and physical. And that is what the Schwarzian theory is actually describing. Now, I should also mention that the semi-classical regime of this theory can be found by setting that big C constant here to go to infinity, of course. And I should also mention that this big C has the dimensions of length. It gets its dimensions just from that A parameter that was here because the 2D Newton constant is dimensionless. And that means that you expect just by power counting renormalizability that quantum effects should be imported in the IR instead of the UV in this model. So we will see that happening later on. Okay, so now that we know that JT gravity reduces to an integral over boundary frames f of tau, what shall we compute with it? Now, during this talk, the main thing that I will need for later on are boundary correlators of the thermal theory. So I imagine computing some path integral that looks like this. So I imagine inserting some operators that are functionals of this reparametrization f, and I will tell you in the next slide what I will choose here. And I use this Schwarzian derivative action here as the action. And then I'm doing a path integral over all reparametrizations with a suitable measure here that I will not tell you more about. So I mentioned here that I will be mainly interested in the thermal theory. Now, what I mean by that is that this Poincaré time coordinate f, I write it as the tangent pi over beta of a small f reparametrization. So this is the Euclidean version of the relation between the Poincaré coordinate and the black hole coordinates that I mentioned a couple of slides ago. So that was a hyperbolic tangent. That was Lorentzian that I mentioned there. This is Euclidean. So I write the big F in terms of small f like that, and then the Schwarzian derivatives, well, they satisfy this simple relation as well. Now, the integration manifold that we want to integrate this thing over is diff S1 mod SL2R. Diff S1 means that the small f is just reparametrizing a circle. So the small f satisfies these two properties to be a proper reparametrization of the circle. If you go once around the proper time circle, you should go once around the f time coordinate circle, and it should always have a positive derivative. So that's what the diff S1 means. And then modding out by SL2R, so this is this SL2R, this Möbius transform action on the Poincaré time coordinate. This just comes from the isometry group of ADS2 to begin with. So if I compute this path integral and I do a rigid SL2R isometry transformation on my entire setup, I will get the same answer. And I choose to mod out by this. So that's what this modding by SL2R means. We identify these configurations. So this is the setup.
Can I ask you a question?
Yes.
So, sorry, it's still about boundary conditions. So
yeah.
Can we just go one slide back, please?
Yes.
Yeah. So the boundary condition, so the dilaton phi has some fixed boundary value. That's your boundary.
Yes, yes. Along that entire curve, it's fixed, and it's some number that I parameterize as a divided by 2 epsilon as epsilon goes to 0. So it's a very large
f
value.
Then is what? Is part of the metric, or where is f coming from?
F was the Poincaré coordinate parameterized as a function of some proper time. So I define a curve, f of tau, z of tau, where f and z are the Poincaré radial and time coordinates. So f was my choice for Poincaré time.
I understand, but in the original formulation, you had a path integral over the metric and dilaton. So should I think of f as coming from the metric?
Yes, definitely, yes.
But I'm still confused about this. So
because it's a diffeomorphism that becomes physical. So I personally really like this analogy with Chern-Simons and WZW. So the WZW field actually comes from a large gauge transformation in the Chern-Simons theory. So this is the same. So this is a large gauge transformation. So a large or a boundary reparametrization in the gravity language, coming from the bulk diffeomorphisms. So it's the only gravitational degree of freedom left in this model.
But they're large in the sense of some, I mean, usually by large, we mean some instanton type thing, but here
by large, I mean that it acts on the boundary.
I see.
Very analogous with WZW. And actually, this is more than just an analogy, because you can write a first order formulation of this theory where it corresponds to an SL2R BF theory.
Mm-hmm.
And the boundary model will be a particle moving on the group manifold.
Mm-hmm.
And that story or that link is just the dimensional reduction of the Chern-Simons WCW duality.
I see, that's interesting.
So it's literally
the boundary condition on the metric you put before you reach this curve is not that the metric is frozen at the boundary, it's something else.
No, it's basically Pfefferman-Graham gauge. I'm doing the same thing you do generically in holography, and that asymptotically the metric starts out being Poincaré, and then in the subleading corrections as you move inwards, you can see deviations from that. That is the boundary conditions.
Subleading.
Sorry?
Is that right?
Sorry?
Oh, sorry, I got cut. So is F the subleading term then in the metric?
Well, it parametrizes.
That's what I mean. So you're saying it's so asymptotically it's still ADS2, but then there is some small deviation. I see. And does this
but the geometry is
Alessandra
everywhere.
Castro and friends, and maybe Grumiller was also here. they wrote down some boundary conditions for ADS2 once long ago. Does this fit that kind of classification?
I'm not entirely. Which papers are you actually referring to now?
There was one by Grumiller and Castro and maybe other people. Daniel should be here, so maybe he can tell. But basically, it's spelling out the Pfefferman-Graham for ADS2, which is slightly special.
Well, yes, then this should be contained within that statement because this is contained in the Pfefferman-Graham gauge.
Okay,
it's the second condition that's specific to this model. And that's actually the one that gives interesting boundary dynamics.
All right, thanks.
Okay, so we decided that we wanted to compute this kind of path integral. So I explained to you what the integration space and so is. So now the main question is what kind of operator should we actually insert in this kind of expression? Now, for inspiration, let's first consider a massive scalar field in the bulk of ADS2 and consider its asymptotic expansion. So I've written here phi as a function of big Z and big F, so the Poincare coordinates. And then, of course, asymptotically, as standard in holography, it has this asymptotic form. So Z to the 1 minus delta, where delta is the weight of this, of the dual field, and then the boundary value of this field. Now, because at the boundary, this big Z is related as epsilon F dot, where F was this Poincare reparametrization, I can write it in the second way. And then I can define a new way of writing the boundary field like this, by just having an epsilon up front here. So a local or a proper radial coordinate instead of the Poincare radial coordinate. And then the generating functional for correlation functions of this system can be written in this way, as is usually the case. So the first line is the Poincare coordinate line. And then in the second line, I have just replaced everything by the proper time coordinates and the proper time boundary field. So this phi tilde gets replaced by phi using this identity that I wrote here, and then you just track the transformation of the measures and you get something like that. So that means that with respect, if I define everything with respect to proper time, then this object is a natural two-point function. It's a reparametrized CFT two-point function. And this will be the operator that I will insert in the Schwarzschild path integral. So it's a bilocal operator. It depends on two times, tau1 and tau2, and it's parametrized by one number. So it's the conformal weight of the field that you start with here. And I will call it L just because, we called it that in our paper, so I'll stick to that notation. So this is the kind of operator that I want to insert in the Schwarzschild path integral. It's in terms of the big F, the Poincare time coordinate. I can also rewrite it by using big F is a tangent of pi over beta small f. In this way, in terms of the black hole time coordinate small f. Now, this looks like a very complicated task to compute these path integrals, but there are several ways of doing it. Before mentioning this, I should also mention, by the way, that there's another origin of this operator. Instead of using this boundary values of a CFT field, you can also think of this as a boundary anchored Wilson line in the first order or the gauge theoretic formulation of this gravity theory. So imagine you have a two-dimensional bulk and then you have a Wilson line with two endpoints, and those two endpoints are on the boundary. Then this defines also a bilocal operator, and you can show that this actually leads to the same operator in a suitable representation for this operator, of course. So in any case, that is just to say that this is a natural thing to consider. So as I mentioned, it looks quite complicated to solve this path integral because the operator is bilocal and looks complicated. The action is higher derivative, so it looks like a very complicated problem. But several approaches have been developed by now to obtain these correlation functions. So I mentioned here, or I give just an overview of some of them. So the first one was by doing a field redefinition where you set f dot equals to e to the phi. And then you can relate the system to a 1D Liouville calculation. A second approach, which is something that we looked into a couple of years ago, is by looking at two-dimensional Liouville CFT between identity branes, between CZ branes, and then taking a suitable parametric limit of that system. And then you can show that you find this Schwarzschild path integral with these specific operator, bilocal operator insertions. As I also mentioned just now, there's a gauge theoretic SL2RBF view on this entire story, and from that, so using gauge theory techniques, you can also get these correlation functions. Also, there's a limit of a particle moving in ADS2 in a magnetic field, where you take this magnetic field to go to infinity. That also makes contact with this description. That was also developed by several authors 2 years ago. And then finally, there is a way of getting to these correlation functions, or to this theory to begin with, from as a parametric limit of the minimal string or Liouville gravities. So I won't mention any of these derivations. I will just mention the final results. And well, you have to believe me, but they agree between all of these views. So we're quite confident this answer is correct by now. So the result for a single bilocal operator inserted in the Schwarzschild path integral, it looks like this. So there are two dummy integrals, two integrals over E1 and E2, two energy integrals. There are two rho 0 E's, where these are densities of states, and they're this famous sinh square root E density of states that you have in the Schwarzschild theory and in JT gravity. And then there are these Hamiltonian propagation factors, so e to the minus the difference between the taus times the difference between the energies, and then a Boltzmann factor for the other one. And then you have factors that connect the two energy variables, which is a product of 4 gamma functions. So whenever I write this gamma plus minus, I mean you have to take the product of all 4 combinations. So there's a product of 4 of them here in the numerator. And then this z is the Schwarzschild disk partition function that we just divide by. So this is a very explicit expression that you can plot numerically to see, well, what it looks like. So there is an explicit answer given as this double integral. Now, for the purposes of the talk, I just want to mention that, so this is the canonical ensemble result, it's for a fixed beta. So you can easily go to the microcanonical ensemble by inverse Laplace transforming, but okay, the Laplace transform is just written here, so we just strip off the E2 integral, and that will be the microcanonical result. So this will be important for what I mentioned later on. Okay, so that was everything that I had to say on the Schwarzschild theory and its bilocal correlators. So now let's go to the main goal of my talk, which is to define and to compute bulk observables in this theory, in JT gravity. And of course, I will exploit this boundary Schwarzschild description. So let's first think a bit about what it means to define a bulk observable, which would be a diff invariant operator in quantum gravity. And as is well known, this requires care. For instance, when you do quantum field theory in curved space-time, you might say, or you might consider a scalar field phi of x, but when you consider that operator in full quantum gravity, you actually have to specify what you mean by that label x. You have to define it in a geometrically invariant way. So the bulk location needs to be defined intrinsically or in an invariant way. And because we're doing holography, it's actually, of course, preferable to do this in a boundary intrinsic way. So we wish to anchor all of the information on bulk locations to our holographic boundary. Now, there are many ways of doing that. So we just make a choice, and then we compute with the bulk observables that we define in this way. So we will make a choice here, and I will use a kind of radar definition to define the bulk point. So given two boundary times small u and small v, so they're proper times on the boundary clock, I define a bulk point big U and big V, so these are the Poincaré light cone coordinates, from the off-shell boundary parameterization big F. So for any big F in the path integral, I can do this construction using this definition. So the Poincaré U coordinate is just F of the small u, and Poincaré V coordinate is just F of the small v. And small u and small v were coordinates that I defined on my proper time on my boundary clock. So if you draw this graphically, this is the kind of figure you would get. So in blue and red, I have drawn two off-shell boundary clocks and their ticking patterns. And then the two ticks where I draw these two lines are the small v and small u coordinates. I send in and extract null rays, and that construction defines for me a bulk point, big U, big V. But of course, as I show here, and also as you see here, that the location of that bulk point is dependent on the precise form of this boundary parameterization or this boundary clock. So this is a choice. Other choices exist, of course, but this is a choice where the computations can actually be done exactly. So that is why, of course, I'll pick this choice and we'll see what we get. So using this definition of bulk point, any observable is now defined in this way, where there is implicit metric dependence or implicit F dependence, reparameterization dependence there. So that means that if I consider, for instance, a correlation function of operators that I define like that, because there's this implicit dependence on the geometry F, you get additional contributions, for instance, in commutators. And this was nicely shown a couple of years ago in a paper by Donnelly and Giddings in perturbation theory. So this is the definition we will use. Now, to actually supply these operators to begin with, I will couple JT gravity to a bulk matter action, and I will take massless scalar fields for simplicity. So we take the previous JT gravity action that depends on the metric and the dilaton as before, and then I just add a massless scalar field to it. And for instance, for the simplest thing we can compute, and well, the only thing that I will really talk about is the matter's two-point function. So I just take the phi two-point function in this theory. Now, if I first do the CFT, or sorry, the matter's path integral, then of course this matter's two-point function has a well-known form. So it's the log of the distance between the two points. Now I have this cross ratio like form here because I'm considering this CFT two-point function on the upper half plane, because we have this holographic boundary and we impose Dirichlet boundary conditions on this scalar field phi, and that explains the denominator here. So those pieces are just contributions from image charges. Now this was done in a fixed frame big F. So this is actually, well, the definition of the bulk point that is happening here. And then as a second step, we take this matter two-point function, and now we path integrate this thing over the metric and the dilaton field, which of course just boils down to a path integral over this F reparameterization. So I'm proposing here a two-step process where we first integrate over matters to get a gravitational operator that we in turn insert in the gravitational path integral to get the final answer. And that will be the exact answer. That will be the answer that includes all of the quantum gravity effects as well. So that's the strategy. Now, if we try to insert this thing in the Schwarzschild path integral, it looks very complicated. I only explained to you that we can get things that look like this, that we know the answers of things that look like this. But of course, there's a simple trick. I can write this log of a cross ratio basically as a double integral of the thing we know how to compute, of which we have an actual answers. And this trick actually coincides with the HKLL prescription of bulk reconstruction to map bulk operators into boundary operators. So the HKLL construction writes a bulk operator as an integral over some kernel times boundary operator. Now for this specific case, for a massless scalar field in 2 dimensions, that kernel is just a Heaviside that restricts the range of that T and T prime integral that's here. So this is the bulk two-point function on the left-hand side, double integral with the HKLL kernels, and then the boundary two-point function on the right-hand side. So this matches with that. But now, because we see that this is just a double integral of something we know how to compute in the Schwarzschild path integral, well, we just have to do that double integral of the final answer of the bilocal correlator in the Schwarzschild theory. So that's simple to do. And this is the answer you get. Well, it still has 2 E integrals, and then it has some oscillating dependence on both Z, Z prime, and the time difference between the 2 bulk points. Z and Z prime are the radial locations of the 2 bulk points. Well, if you try to analyze this thing, what it looks like, it doesn't do anything too drastic. So what I've drawn here is I pick one point somewhere. So I've drawn the Euclidean, or I've computed the Euclidean calculation, of course. So I pick one point here, which is this black dot. And then the different colors represent different time separations to the second point. And then this graph is this bulk two-point function as a function of the radial coordinate of the second point. And as you can see, well, if you follow this blue line where this time separation goes to 0, you can see, well, of course, a singularity developing. So, and that is actually all you have in these correlators. So they're actually quite well behaved. You get singularities in Lorentzian signature only at light-like separated points, and the singularities are log singularities. And the reason that they're log singularities are just because if you stare at the operator itself, well, it explains itself why it should be like that. So this is not too hard to do. Now, I should also mention that you can generalize this calculation, not just to the scalar field, massless scalar field two-point function. You can take matter CFT primaries in the bulk, and then you are led to considering the Schwarzschild path integral of these things, which are of course of the same form, and we can do them exactly. And you can also generalize to massive bulk fields as well. So for massive bulk fields, the matter 2-point function is a 2f1 hypergeometric function in terms of this, invariant distance that contains a cross ratio as well. But there is a way to write this thing again as a multiple integral of things that look like this, where you can again use the same tricks. So everything ultimately boils down to these expressions f dot over f minus f squared to some power. And the generic picture we get from analyzing the resulting expressions you find from these types of calculations is the following. So I've drawn, the Penrose diagram again. So imagine we put one bulk operator at this red dot, and then what I've drawn here is the behavior of the 2-point function as you move the second point around in the bulk. And close to the light cone singularities, and this includes reflections of the holographic boundaries, you're close to these UV singularities, to these logarithmic divergences. Then there is some intermediate region that I color green here. And then there is an IR region where the points are widely separated, where you have strong quantum gravity fluctuations. So where this 2-point function deviates strongly from its semi-classical result. And that happens at late time and at long spatial or large spatial separation. So that is the generic picture we get from analyzing these types of bulk correlators. Now let's try to analyze some of the physics that we have here. So the first thing that I want to comment on is about bulk locality. So I have defined my operators to be diff invariant. I didn't define them to be local in the sense that I didn't demand that they commuted at space-like separation. But because the commutator is just the difference of two orderings for the bulk 2-point functions, I can just check whether this property is true or not for the operators that I have defined in this way. And it's satisfied. So this means that these operators are mutually local operators in the full quantum gravity in the bulk. Now, this is a bit unexpected. And I also like to refer to this paper from Maldacena and collaborators for another construction of diff invariant bulk operators that also turns out to be local. So what this means is that JT gravity with matter operators or with a matter sector in it is actually more local than you generically expect in quantum gravity. So it's easier to construct operators that satisfy bulk locality in this way. So that's one physical conclusion that we get from these operators. And then a second conclusion, and I mentioned this already before, is that so for large spatial separations, you get strong quantum gravity effects. So the near horizon region, where you put one of the operators close to the horizon, is like an IR region, and it's similar to the late time regime. So strong quantum gravitational effects and deviations from Rindler correlators, where Rindler is, of course, the near horizon geometry of any black hole. You can get further intuition into this statement by, instead of considering a bulk correlator, you consider the same operational definition, but now of the infinitesimal distance squared. So you take a limit where you take the geodesic distance between 2 points in this geometry where we define bulk points in this radar definition way. You find that the conformal factor of the metric you define in this way is again just the same combination. And that means that close to the horizon, which means that u minus v is large. That's the same as the large time regime of the Schwarzschild 2-point function. And indeed, from that perspective, you also see strong deviations, strong quantum gravitational effects there. And this might have implications for formulating information paradoxes, because what we have illustrated here is that if you insist on defining your bulk operators in a diff invariant way, then this on its own can already lead to the near horizon region being very different from Rindler space and a breakdown of effective field theory. Now, I should also immediately mention, of course, the reservations that are present here. So first, it is for this specific model, for the JT gravity model, which is a kind of a special gravity model. On the other hand, I have mentioned at the very beginning that there is some sort of universality for JT gravity. And then secondly, it is for these specific bulk operators that we have constructed using this radar definition. So presumably less natural bulk operators exist that might not have this property. So yeah, we just don't know, because these are the only operators for which we can actually explicitly calculate this Schwarzschild path integral. Other ones we might be able to do in perturbation theory, for instance, but that is not enough to get to the near horizon or late time regime. But it would definitely be very interesting to understand how other operators behave, or how other bulk operators behave in this respect. Okay, so now that we have the bulk 2-point function, and in the second part of my talk, I want to analyze the spectral content of this bulk 2-point function, because this probes the black hole thermal atmosphere, and in particular, this is what leads to Unruh bath physics. So I'll briefly talk about two quantities. The first is a detector measurement, an Unruh DeWitt detector measurement, and the second is the bath spectral energy density. So firstly, the detector. So I will now define an entire trajectory of a detector, a time-length trajectory of a detector, of an Unruh DeWitt detector, in the same operational fashion that I have defined bulk points up to this point. So I define my detector to be at a fixed radial location, small z, and then I use this radar definition again to define my entire trajectory of the world line. That, of course, depends on, again, this off-shell f of t. So just like before, I have drawn two examples here, but now I use them to not just define one point, I use them to define an entire time-length trajectory in the bulk. And along this world line, I will introduce the interaction, the typical interaction that Unruh and DeWitt considered, where I have a quantum mechanical degree of freedom that I call mu, and I couple it linearly to the bulk matter quantum field phi. So this is the definition of the Unruh DeWitt detector. And now I will compute the transition probability for this detector to go from its ground state to an excited state of energy small omega, without any information on the excitation of the QFT matter state. So this leads to this transition probability in this form, in first order quantum mechanical perturbation theory, where the detector goes from the ground state to an excited state, and the quantum fields go from their ground state to some state that I don't specify. I sum over all of these possible states, and I take, well, the first order interaction Hamiltonian here. From this transition probability, as is usual, we just define the transition rate, which is just, well, given by Fermi's golden rule, basically, and this is the expression Unruh and DeWitt got a long time ago. So it factorizes in terms of something that the detector is doing, which is not interesting. It's detector physics, which is not what we want, or what we're interested in. And then we have some Fourier transform of the bulk CFT matter 2-point function. And well, now we immediately see, what I'm trying to do. So we have the bulk matter CFT 2-point function here, and we have already computed it in the previous slides. So we'll just insert this thing again in the Schwarzschild path integral, and then just Fourier transform the results to get to this transition rate, but now including all of these quantum gravitational effects that the Schwarzschild theory is encoding. Now, for simplicity, I will mention the results on the next few slides in the microcanonical ensemble. So for a fixed energy big M black hole state, not the canonical. Of course, as I mentioned previously, canonical and microcanonical are simply related by just one more Laplace transform that you need to do to the results that I will mention here. So this is what the answer looks like. So for this response rate. So it's a product of several factors. So the first factor is this 2 times sine z omega divided by omega squared. This is not an interesting factor. This is just an interference factor coming from the image charges across the ADS2 boundary. So it's there, but it's not super interesting. The second piece is an interesting part. So it has this sinh square root m minus omega. So this, of course, well, it just comes from taking the Fourier transform of those Schwarzschild bilocal correlators. That's why there's a sinh, of course. And then a product of 4 gamma functions, and then a Heaviside function. And the combination of all of that is the matter emission probability. And in particular, notice the presence of this Heaviside function, m minus omega, because this signals a back reaction effect. Omega was the energy that our detector absorbed, and m was the black hole mass. So that means that no energy greater than the original black hole mass can be emitted to the detector probe. So this is a back reaction effect. This is, of course, something that the standard quantum field theory in curved space-time calculations cannot get to, because we need back reaction effects in order to have this. But here we find this because we treated the system exactly. And as a check on this weird-looking function that I call the matter emission probability, in the semi-classical regime, where I take a very large black hole in Planck units, and I have a very small energy absorption compared to the mass of that black hole, you can just use Stirling's formulas on these gamma functions, and you find that this matter emission probability just reduces to the Bose-Einstein or the Planckian black body spectrum. So this thing generalizes it by including the quantum gravity effects as defined by the Schwarzschild path integral, or the JT gravity path integral on the disk topology. So that, well, in the next couple of slides, I will talk about how to generalize this to go beyond the disk or beyond genus 0, as we have learned in the past couple of years that higher topology is actually very interesting. So now I will talk about higher topology corrections in the gravitational path integral to this detector response. So as I mentioned, including higher topology is important, and we have learned that especially in the last couple of years. But one typically ignored these in the past because they are strongly suppressed by this kind of factor, where G is the genus of the surface, and S0 would be the extremal black hole entropy. And such a factor you would get by including next to the JT gravity action also the Einstein-Hilbert term. And then, of course, the Einstein-Hilbert term is topological. It is just the Euler character. So in the path integral, this just gives you this factor. And then at higher genus, as long as S0, the extremal entropy, is sufficiently large, which is something we will assume, then higher topology seems very suppressed. So we shouldn't consider it. But it can be important in parametric regimes where this suppression of higher topology is actually compensated by an enhancement, such as late time or small energy separation. And we have learned a couple of examples in the past few years. So for instance, replica wormholes that are needed to find the page curve, so to find the declining part of the page curve, that one requires higher topology. And also, the late time average correlation function of a boundary theory has this ramp regime. And from the bulk perspective, that one also requires higher topology, in particular the annulus contribution. So we have learned recent examples where higher topology is very important. Now, so the genus expansion generically is asymptotic, and it requires a non-perturbative completion. And now I will use this result from Sept, Schenker, and Stanford from last year, that for the specific case of JT gravity, the genus expansion can be completed into a double-scaled random matrix integral. So I will use this now to analyze what the effect is of higher genus contributions on this detector response. Now, in that same paper, Sept, Schenker, and Stanford studied this for multi-boundary amplitudes. And then later on, we looked at that, and then it was studied further in a paper by Phil Saad. These higher genus effects were studied for boundary correlators. So these would be the same correlators that I mentioned in the beginning for the Schwarzschild theory. And without going into the details, what these computations show is that the higher genus contributions only correct the n density factor in the correlators. So for instance, in the 2-point function, it was a double integral of two energies and then some Hamiltonian propagation factor, some gamma functions. And also we had twice the Sinch spectral density here. So rho 0 E1, rho 0 E2. That's what we had in the 2-point function. So the higher genus contributions and random matrix contributions are fully captured by just replacing this product by the paired density correlator in the random matrix ensemble that describes JT gravity. So that is what these calculations lead to. And then in turn, this paired density correlator is very well approximated by the Gaussian unitary ensemble random matrix structure. So the GUE paired density correlator has this famous structure. And as long as S0 is sufficiently large and E1 is close to E2, which is, well, where we will find all of the effects we want, then this is a very good approximation. So where this rho is, well, this rho is in principle the exact single density operator of the matrix ensemble that describes JT gravity. So these are the kinds of results that this random matrix perspective on JT gravity leads to. Now, given this pair density correlator, what are the important physical features of this that is well known in the random matrix literature? Well, it has a level repulsion. So if the energies E1 and E2 of this structure limit to one another, it has quadratic level repulsion like this. And then it has high frequency wiggles, as you can see, because there's a sign and there's rho here, and that rho has an e to the S0 in it. So there are high frequency wiggles in this structure with a typical spacing of e to the minus S0. So a very small spacing if F0 is very large, which is what we will assume. Now, this is just the structure of this random matrix story, and that is what has been shown in these papers. This structure has a geometric interpretation, of course, in terms of higher topology and JT gravity. So what I've drawn here is the disk diagram, so the genus 0 diagram, with one boundary 2-point function. So the points where this blue line hits the boundary, those are my 2 points, and I've connected them with this blue line. And then we are instructed to sum this over all higher topology that we can add to it, all higher genus structures. And these higher genus contributions, they fall into different categories. So the middle diagram consists of higher topology that is disconnected between the two sides of that blue line, while there is another class, this last diagram is a representative of that, where they are connected. So there's like a tube connecting both sides of that blue line. And these geometric structures, they match the structure we had on the previous slide of the pair density correlator, because if I go back, the pair density correlator had a disconnected piece and then a connected piece. So that structure is mirrored geometrically here. Okay, so this was all for the boundary correlator and its higher topology or its higher genus contributions. Now we are interested in, or during my talk, we are interested in a bulk correlator. So we need to decide, or we need to find out how to deal with higher topology for the bulk correlator. Now, since the bulk correlator was written through the HKLL description and the radar construction in terms of a boundary correlator, the proposal we make here is that we just insert these higher genus effects directly in the boundary correlator and then go into the bulk using the same HKLL radar construction. So this is a proposal, but it is a proposal that nicely gives you the physics you expect, and it has the correct limits as well. But of course, there might be other definitions here on what to do with higher topology for bulk correlators, but it is a highly non-trivial problem. One reason that it is, well, or to immediately see that it is non-trivial, this radar definition that we had was intrinsically Lorentzian, while this higher topology contributions is intrinsically Euclidean. So if you think about defining a bulk correlator and adding higher topology, it's not as straightforward to think about what you should be doing. So we believe that this rule actually, looked very plausible to us, and it basically promotes the HKLL reconstruction formula to be also valid when including higher genus corrections. That's another way of stating this. Okay, so, well, given that we're going to try this, well, the final detector response rate is modified only in a small way. The only place where it gets modified is that now we have a pair density correlator here, while previously, well, you can see what we had previously, because this rho m minus omega, if just at genus 0, this would be rho 0 m times rho 0 m minus omega. So the row of m's drop out, and we just have rho 0 m minus omega. So this is the generalization you get if you assume this definition of higher topology for bulk correlators. So now let's just make a plot. So the response rate is up to that interference factor that I don't care about, is given by this bluish shaded region. So the line that's on top here is the one where we don't include higher topology or higher genus effects. And then what you can see now is that this response rate, it has these high frequency wiggles, and then it has this quadratic level repulsion. And this has a nice interpretation as a product of probabilities. So, well, these factors, rho m, m minus omega, rho m, you can think of these as the probability of the black hole system containing two levels spaced by omega to begin with. And that is something that, well, you previously didn't have. So if you imagine that you have a chaotic black hole that emits this quantum to begin with, well, then, for instance, if the black hole system is chaotic, it cannot have two energy levels at the same energy to begin with, to start emitting a particle. So that is the effect you see here. So it's kind of like, well, qualitatively, it's like the genus zero effect gets multiplied by the probability of this chaotic system to emit the quanta to begin with. So that is one probability factor. Then you have the probability of the matter emission on its own from such a system, which is roughly, well, it's qualitatively similar to what we had in the disk. And then, of course, this interference factor again. Okay, so now in the final couple of minutes of my talk, I want to talk about the bath energy density, and in particular the bath energy spectral density. So we analyzed this detector response. So that was one observable. Now we're going to analyze a second observable. Now to analyze the energy density, first of all, let me write down some formulas for the energy flux density of the matter system in the bulk. So again, we have the CFT 2-point function. If we take, well, derivatives and then take the coincident limit, of course, we get the definition of the bulk stress tensor density. We know as an operator, in terms of this off-shell frame, big F, what this 2-point function looks like. So just plug it in and you find, of course, that this energy flux density is just a Schwarzschild derivative. And then in the second step, we insert that in the Schwarzschild path integral over this. So with this insertion. So I didn't really mention how you compute Schwarzschild path integrals with Schwarzschild derivative insertions, but they're not difficult to do, and you can find them in lots of the literature. And if you do the Schwarzschild path integral, you find two terms. The first one is the standard Unruh heat bath energy density you find in textbooks if you well, specify to the ADS2 case, of course. And then you have a 1 over big C correction. So this is a quantum gravitational correction to the energy densities. And then the total energy in the heat bath surrounding the black hole can then be defined, well, by taking these two light cone components and then summing them along a spatial slice, of course. So that will be one way of computing the total energy contained in the heat bath, but defined operationally now by summing these local energy densities that are on their own defined through this radar definition. So now I want to get to the spectral energy density. And the way to do that is, again, basically by Fourier transforming the bulk 2-point function. So I want to get to this quantity A dagger A, so the number operator of the quantum field vacuum times omega. So this will be the energy occupation number. I want to get to this. And of course, standard QFT immediately tells you that you can get this by doing a double Fourier transform of the phi, so the bulk 2-point function, which we already computed again. So maybe for the sake of time, so there's a technical remark that I should make here, but let me skip that for now. So in any case, what I wanted to convey here is that the energy spectral density is again given by something we can compute. So again, insert this in the Schwarzschild path integral, and again, first do the disk only, so genus 0 to begin with. So what I've shown here is the energy occupation number as a function of omega, and the red dotted line, the bottom line, is just the semi-classical Planckian black body spectrum in 1+1 dimensions. This is the thing that you find in textbooks on the Unruh effect if you specify it to 1+1 dimensions. And then the blue result is the exact result you get from the calculations that I showed you before from doing that Fourier transform of the bulk 2-point function. And then there's this check you can do, and that was the reason that I mentioned the energy densities in a couple of slides ago, that if I take omega and omega, but after doing the Schwarzschild path integral, after doing the gravitational path integral, and I integrate that from 0 to infinity, I should of course get the total energy stored in the heat bath. But there is of course a second way of calculating it, and I've already shown you how. Take these stress tensor densities and integrate them along a spatial slice. And numerically, well, we have checked that this works out. So this is a check that this thing seems to be on the right, or it's at least consistent. Let me put it at that. And then, okay, so finally, some extensions to show you that this formalism, you can extend it in several directions. So this is the same kind of plot of the Unruh heat bath, but now instead of a massless scalar field in the bulk, we take a Majorana fermion field in the bulk. And again, you see a slight modification. The red dashed line would be the Fermi-Dirac spectrum in 1+1D, and the blue would be the one that includes this Schwarzschild path integral. So again, only the disk. And well, you can give an interpretation on what this actually means. So you see that if you include quantum gravity corrections, you get a slightly higher occupation somewhere in the middle, or at some intermediate values of omega, let's say, but not at very small values of omega. And you can interpret that as that the low energy spectrum of that heat bath has a competition between gravity and the Pauli exclusion principle, preventing any major modifications to the highly occupied low energy levels. So that's one way of reading this figure. Well, this is about some work in progress that we're thinking about now. There are a couple of generalizations to other systems you can think about. One of these is a charged black hole, where the boundary dynamics is altered from just the Schwarzschild degree of freedom, from just this boundary time reparameterization, to also include a U1 free boson field. So I've written down the action here. But then you have to take care of the fact that if you define a bulk observable, next to fixing the coordinate invariance of that, so next to fixing the diffeomorphism gauge symmetry, you should also fix the U1 gauge symmetry as well, which means you should further address this by an electromagnetic Wilson line. Well, in any case, this is something we are looking at, so this is not completed, of course. And then a second extension you might try is to extend this to JT supergravity. Now, JT supergravity, I'm talking only about n=1 case, so the lowest amount of supersymmetry, has a very, very similar structures to the ordinary JT gravity. In particular, it's fully determined by the boundary dynamics, which is a super Schwarzschild then, describing reparameterizations, not of a circle, but of a supercircle. And I've written out these super reparameterizations here. And then you can try to follow the story that I mentioned up to this point. So you need to give an operational definition of a bulk point. Here, the statement becomes a bulk point in superspace. And you need to do that to fully fix the S-diff gauge symmetry. And you get a very analogous structure. You can write your matter operator, which is usually defined in terms of super Poincaré coordinates. Now these super Poincaré coordinates are on their own determined in terms of 2 times on the boundary superclock, which would be tau theta and tau prime theta prime, as I've written here. So you can actually, there's a perfectly analogous set of statements in this case. And no surprise, the bulk correlators are fully determined in terms of the super Schwarzschild boundary correlators. And one physical effect I should mention here, but well, you know this in advance if you think about it, is that this supersymmetric case differs from the bosonic case only in the quantum corrections. And this makes sense because the classical bulk black hole solution has, of course, no fermions turned on. Okay, and then for my, well, final slide before I reach the conclusion. So the past few slides have been about, at the disk level, this energy spectral density. You can again go beyond the disk, include these higher topology / random matrix effects here. And I'll just show you the plot here. So this is again, omega and omega, so the energy occupation number as a function of omega. And if you go to very small omegas of the order of the inverse levels, well, as of the order of the level spacing, which is e to the minus S0, you see, that's what this blue curve is, you see these very high frequency wiggles and this quadratic level repulsion. So the green and red curve, well, they're not super interesting here, they're doing the same thing, but they're the semi-classical, and the disk or the Schwarzschild result, you can see that they agree here. They will differ if you go to higher omegas, as I've shown you on the previous plots. But you can clearly see these very, very small omega effects coming from these random matrix or higher topology effects appearing here. Okay, so let me conclude. So JT gravity is a toy model of quantum gravity, but it strikes an ideal balance between, I think, relevance and solvability. And by relevance, I mean that it's, well, I mentioned the motivation in the beginning. It's the low energy sector of all SYK type models. It is one of the most basic, non-trivial holographic 2D gravity models, and it is universal in the near extremal near horizon regimes of higher dimensional, well, of large class of higher dimensional black holes. And by solvability, I mean that the gravitational degrees of freedom in the bulk, they fully reduce to this boundary time reparametrization, big F that we had, so the Schwarzschild degree of freedom. And we have an explicit and analytic solution for correlation functions, non-perturbatively in the Newton's constant. And also, and that's some of the recent developments, we have an explicit understanding of how higher topology works and the resulting random matrix effects. And during this talk, I have shown you some results on calculations on bulk two-point functions. And again, I emphasize the physical conclusions are dependent on the specific definition that I took, but it is one where we can get exact results for. And those bulk two-point functions, they exhibited bulk microcausality. And I also showed you how you get gravitational corrections to the Unruh heat bath and the detector response. And in particular, this universal random matrix effect of level repulsion at ultra low emission energies. So I think JT gravity is an ideal test case theory to study conceptual questions about quantum gravity. So thank you.
Thank you, Thomas.
Thanks.
So questions?
Yeah, well, you mentioned the n=1 supersymmetric extension of JT. What about n=2?
That is harder. So, well, if you want to do, so I mentioned this here because I want to sort of pursue the same program. So I need in particular the boundary two-point function. And they are known for n=1 JT supergravity, but they are not known explicitly for n=2 JT supergravity. So that would actually be very interesting to get an exact expression. But yeah, I didn't manage to do that on a technical level. So, but yeah, it would be interesting, especially because n=1 in 2 dimensions and the n=0 case are very similar. But as soon as you go to n=2, you get this additional U1 group and so on. So there's much more new things happening there. Yeah, so I think n=2 and higher, but mainly n=2 probably would be very interesting to understand.
Any other questions? Right, if not, let's thank Thomas again. All right, thank you, Thomas. So
stop sharing.
Yeah, okay, you can stop sharing. Okay. All right, so we'll reconvene in 10 minutes for Vijay's talk, basically. Thank you, everybody.